So hello, in today's video I would like to give an example for the multiple linear regression, and in particular I would like to talk about the transfer length method. So I do not want to go into detail about the transfer length method, but just give a very brief overview, and on Wikipedia there is quite a good article about it. And if you're interested or need it, I think you can read the article. But just in short, what is done here in the transfer length method, one is interested in determining the specific contract resistivity between a metal and a semiconductor thin film layer, and therefore one deposits pads at the surface of a semiconductor thin film, and one measures then the resistance between two adjacent pads. This causes that the distance between the pads increases, and therefore also the measured total resistance increases. And from this plot one can determine the parameters, the specific contact resistivity between the metal and the semiconductor, as well as the transfer length. And the transfer length is the length here up to which current passes from underneath the semiconductor layer into the metal. And the more advanced method of this transfer length method is the circular transfer length method. So here, instead of having rectangular pads, one has circles, an inner circle and an outer circle, and the gray areas, they are metal, and one changes the distance between the inner and outer diameter, and therefore also the totally measured resistance increases. And this has certain advantages when compared to this approach, and the advantages are covered within the article. I will not cover it in this video. However, from this geometry one can extract an equation that depends on the outer diameter, and the distance between inner and outer diameter, d, here is varied. One can do the same thing when the inner diameter is kept constant and the outer diameter varies, as it is described in the following example. So here on the page there is also a practical example, and here the same equation as above is written in a short notation, and you see that there is an expression given for A, for B, and A and B do not depend on D, but here as multiplicators we have the function G and H, which depend on D. And as covered in my last video, one can or the other video in this playlist, one can make several measurements at different distances d, and then one ends up in this matrix notation. So we have, for example, here 10 measurements were done, then we have determined G and H at distance 1, A and B are here in this vector, and here we have the error vectors, they are due to measurement errors. And this is the same equation in more compact notation, and this is the equation to extract A and B. And if we know A and B, then we have an equation. First we have a fit for the measured data points, and the other thing is, if we know A and B, we can calculate the specific contact resistivity and the transfer length. So here an example is given in Octave, which you can try if you wish. So Octave is free software, but for more illustrative purposes, to see better the matrix multiplications, I've decided to do it in LibreOffice, which is similar to Excel. So I think everything I'm doing here works also in Excel, and I have already prepared a screenshot of the Wikipedia article to not have to such that do not have to switch between windows every time. So here the first column is G. Here are the G functions evaluated at D1 to D10. So we have already collected values for D1 up to D10. Here are the corresponding resistance measurements, and here you see a plot of resistance versus pad diameter difference D. But now go back, to function G. Let's evaluate this function here. So it is the logarithm, the natural logarithm of the inner diameter, which we have here, which is in this case, I think 200 plus D divided by inner diameter. So everything should be closed. Now do the same with H. H equals, it's 1 over the inner diameter, it's 200, plus 1 over 200 plus difference between circle diameters. So the next step is we have to calculate this matrix product here. So basically this the x vector, the x matrix is given by these two columns here, and it's transposed basically as well. So let's first calculate this matrix here, and it should be a 2 by 2 matrix, because the transposed matrix of this matrix here is a 2 times 10 matrix, and a 2 times 10 matrix multiplied with a 10 times 2 matrix is a 2 by 2 matrix. So let's enter it. The command is matrix multiplication. Then here we have to enter the transposed matrix, which corresponds to the command m transposed or m trans. Let's do this. Then a semicolon, and then here again enter this matrix. And I confirm now not by just hitting enter, but by pressing Control Shift Enter. Very well. Here we have now the matrix x transposed times x. Now we have to invert this matrix. Therefore, we do the same. The inverted matrix of this matrix should also be a 2 by 2 matrix. So there is a minf is the inverse of a matrix. Select the matrix here, and here also confirm with Control Shift and Enter. So now this expression here, x transposed times x inverse, is evaluated. Now we evaluate the matrix vector product on the right side. So therefore, this the result of x transpose times r is a 2 by 1 matrix, so 2 entry column vector. So we have to select here 2 cells. Again, command matrix multiplication. So the inverse matrix of this here then semicolon as a separator, then this is the R vector. Confirm with Control Shift and Enter. Oh, I made a mistake here. Oh, sorry, this is the not the inverse but the transpose. So I will do it again. Mistake, sorry. In multiplication and transposed. Mark the R vector. Sorry, again, I forgot to highlight 2 cells. Now it's done. And finally we have to evaluate this vector here, which contains A and B, the coefficients we are searching for. Now again select 2 cells. This is a matrix multiplication, and we have to multiply this matrix here with this vector. Again, confirm with Control Shift Enter. And now we can check our result. Let's do the fit. So the fit is coefficient A. Then we fix the coefficient A by pressing F4. Now the dollar signs appear and they tell us that this value is fixed. So if we move down, the cell reference will not move with down going cells accordingly, times J function evaluated at D1 plus B with also dollar sign times H function. Looks good. So what have I done here? Let's repeat again. Here I just plotted this function here, R total. First, here we have the value of A, which is this value here. Then multiplied with function H evaluated at a value of 20 plus value of B, which is still with this value here, multiplied with function H evaluated at value of 20. And then just I copied the formula to the cells below, and this R function is here now evaluated at different values for D. And as you see here, fit looks quite good. The blue squares are the measured data points, and the orange curve is the multiple linear fit. And here, from the expressions of A and B, I extracted the sheet resistance RS, then the transfer length LT, which also depends on RS and rho C, but is not shown in this screenshot here. And finally, I also obtained rho C from the relationship between A, B, RS, and rho C. And basically, that was a practical example for the transfer length method, evaluated with multiple linear regression. Hope you liked the video, and maybe we see each other again during the next video. Goodbye.